There was nothing in the beginning. The universe then began to take shape about 13.7 billion years ago. The circumstances in which this occurred and whether there was a prior period of time are yet unknown. But, combining data from telescope observations and particle physics models, scientists have been able to construct a broad timeline of significant cosmic events. We start by looking at some of the most significant historical events in our universe. It all starts at the Big Bang, when the universe was extremely hot and dense and space began to expand outward in all directions at once. Though the model of the Big Bang states that the universe was an infinitely small point of infinite density, that is only a roundabout way of saying that we don't really understand what happened at that time. The Big Bang is basically the point at which our existing knowledge of the cosmos breaks down because mathematical infinities don't make sense in physics equations. The universe's next trick was to expand extremely quickly. The universe could have grown exponentially in size in the first fraction of a second following the Big Bang, tearing apart previously close-knit regions of the cosmos. The inflationary era, which is still hypothetical, is thought to be the reason why distant portions of space seem so similar to one another while being separated by great distances. The early universe was extremely hot, between 7 trillion and 10 trillion degrees Fahrenheit, just a few milliseconds after the beginning of time. Quarks, which are fundamental particles ordinarily firmly bound inside of protons and neutrons, were free to roam at such temperatures. In a soupy primordial fluid that saturated the cosmos, these quarks were combined with gluons, which carry a fundamental force known as the strong force. Similar circumstances have been produced by researchers in particle accelerators on Earth. The challenging condition, however, never persisted for more than a few hundredths of a second, either in terrestrial atom smashers or in the early cosmos. The next phase of time, which started a few thousandths of a second after the Big Bang, was quite active. As the universe grew larger and cooler, protons and neutrons began to form when conditions were favorable enough. During the first 3 minutes of the universe's existence, protons and neutrons fused together to create deuterium, helium, and a trace quantity of lithium, the next lightest element. Yet, this process ceased as the temperature dropped. 380,000 years after the Big Bang, conditions were finally cool enough for the first neutral atoms to form when hydrogen and helium combined with free electrons. Photons, which had previously run into the electrons, could now move without interference, forming the cosmic microwave background, CMB, a relic from this epoch that was first discovered in 1965. There was no light in the universe for a very long time. The cosmic dark ages encompassed this time frame, which lasted around 100 million years. Because astronomers learn about the universe almost exclusively through starlight, this era is still very challenging to study. It's hard to understand what happened when there are no stars. At 180 million years after the Big Bang, hydrogen and helium started to condense into enormous spheres. This caused their centers to reach hellish temperatures, which ignited the first stars. The scorching photons emitted by early stars and galaxies caused neutral hydrogen atoms in interstellar space to break into protons and electrons, a process known as ionization, which is when the universe entered a period known as cosmic dawn, or reionization. Reionization's duration is difficult to determine. The most that scientists can say is that it ended about 500 million years after the Big Bang, since it happened so early and its signals were masked by later gas and dust. The cosmos gets down to business at this point. Around 1 billion years after the Big Bang, smaller early galaxies started to combine to form larger galaxies, and supermassive black holes started to develop in their centers. When turned on, bright quasars emit powerful lights that may be viewed from 12 billion light-years away. For the following several billion years, the cosmos continued to change. In the early cosmos, regions with larger densities gravitationally pulled matter to themselves. They gradually developed into galaxy clusters and protracted filaments of gas and dust, creating the stunning filamentary cosmic web that is visible today. According to recent findings, the universe's dark matter may have been created by a second cosmic explosion that occurred less than a month after the Big Bang. According to a recent study by cosmologists, the Big Bang may have been followed by a second, dark Big Bang that flooded the universe with enigmatic dark matter. And by observing ripples in the structure of spacetime, we might be able to discern the proof of that occurrence. Most cosmologists believe that the universe experienced inflation in its early moments following the Big Bang, a period of extraordinarily rapid expansion. Since the cause of inflation is unknown, it is necessary to account for a number of phenomena, including the excessive geometric flatness of the cosmos at large scales. A mysterious quantum field, which is a fundamental entity that permeates all of spacetime, is likely what caused inflation. Its field degenerated into a shower of particles and radiation. Some 12 minutes after the universe began, these particles would go on to combine into the first atoms, and hundreds of millions of years later, they would start to group together to form stars and galaxies. Dark matter, however, is an additional component in the cosmic recipe. Again, cosmologists do not fully understand what dark matter is, but they may observe evidence for its existence and the gravitational effects it has on ordinary stuff. In their work, the researchers investigated the characteristics of a dark Big Bang. In order for dark matter to emerge entirely independently, they first proposed the creation of a new quantum field, or dark field, which is required. According to this new theory, inflation eventually fades away. The cosmos subsequently expands and cools to the point when the dark field is forced into its own phase transition and turns into dark matter particles. Only then does the dark Big Bang begin. The scientists discovered that the dark Big Bang had to adhere to particular rules. If it occurred too early or too late, there would be an imbalance in the amount of dark matter in the universe today. But if the dark Big Bang occurred when the universe was only less than 30 days old, it might be consistent with every observation made to date. Most significantly, though, the researchers discovered that a dark Big Bang results in a specific signal in gravitational waves, which are ripples in spacetime that are still sloshing around the cosmos today. So, the theory might someday be put to the test. Pulsar timing arrays, a gravitational wave probe that uses distances to distant pulsars, may be able to solve the problem.